The basic goal of this video is to convince you that we have done most of the hard work when we studied functions from Rn to R. Many properties of functions from Rn to Rm will follow directly from what we studied about functions from Rn to R. For instance, first let us see that if f and g are two functions from Rn to Rm which are differentiable at C, then their sum f plus g is also differentiable at C. Let us go through a proof of this fact. First of all, notice that f is differentiable if and only if all its component functions are differentiable. That means fi is differentiable for all I. And again, these are all happening at the point C. Similarly, we know that g is differentiable at the point C if and only if all its component functions are differentiable. That means gi is differentiable at C for all I. Now, let us try to understand what f plus g is. Notice that we defined f plus g of x to be equal to f of x plus g of x. So, because f plus g of x is equal to f of x plus g of x and f of x is equal to f1 of x, f2 of x, etc. up to fm of x, and g of x is equal to g1 of x, g2 of x, etc. up to gm of x, their sum would be equal to f1 of x plus g1 of x, etc. up to fm of x plus gm of x. And notice that fi of x plus gi of x is equal to fi plus gi of x. In other words, what we have observed after doing all this is that the ith component of the function f plus g is the sum of the ith components of f and g. Therefore, from the analogous result for functions from Rn to R, we know that the ith component of f plus g is differentiable at the point C. And therefore, f plus g also has to be differentiable because all its component functions are differentiable. And thus, we have the result that we wanted to prove. Similarly, we can study about the product of two functions. However, as f of x and g of x will be elements in Rm, we have to be a bit careful about what we mean by product. In other words, we have to take the dot product of f of x and g of x. This function we will define as f dot g. F dot g of x is equal to f of x dot g of x. And that's a function from Rn to R. And we will prove that if f and g are both differentiable, then f dot g is also differentiable. Once again, we use the idea that f is differentiable at C if and only if all its component functions, that means fi, are differentiable at C. Similarly, g is differentiable at C if and only if all its component functions gi are differentiable at C. And notice that this happens for all I. That's very important. Now, let us try to understand what f dot g is. F dot g of x, as we defined, is f of x dot g of x, which is equal to f1 of x, f2 of x, etc. up to fm of x, dot g1 of x, g2 of x, etc. up to gm of x. Therefore, its dot product will be equal to f1 of x into g1 of x plus f2 of x into g2 of x plus etc. up to fm of x into gm of x. And notice that fi of x into gi of x is equal to fi gi of x. Further notice that fi gi is differentiable from the analogous result for functions from Rn to R. And this is true for all I. Therefore, their sum will be differentiable from the result about sums of differentiable functions. And thus, we have the result that we wanted to prove. Using this idea and the idea that a function from Rn to Rm is continuous if and only if all its component functions are continuous, we can show that if a function is differentiable at C, then it is also continuous at the point C. Let us try to see a proof of this fact. As before, f is differentiable at C if and only if all its component functions fi are differentiable at the point C. But if fi is differentiable at C, then fi is continuous at C. And as all the component functions of f are continuous, f itself has to be continuous. And that completes the proof of our theorem. Finally, we are going to prove an analog of the chain rule. However, this time the proof is not going to be so simple. Nonetheless, the ideas used in the proof will be quite similar to what we used when we proved the earlier version of the chain rule. Let's state the chain rule first. Given function f from Rn to Rm differentiable at C and g from Rm to RL differentiable at f of C, the composition of these two functions, g composed with f, which is a function from Rn to RL, will also be differentiable at the point C. Moreover, the Jacobian of g composed with f at the point C is equal to the Jacobian of g at f of C into Jacobian of f at C. Let's try to see a proof of this fact. First of all, notice that f is differentiable at C tells us that limit h tends to 0, f of C plus h minus f of C minus the Jacobian of f at C into h divided by norm h is equal to 0. Therefore, if we define u of h to be the function f of C plus h minus f of C minus Jacobian of f at C into h divided by norm h, then notice that u of h will tend to 0 as h tends to 0. Moreover, we can express f of C plus h as f of C plus Jacobian of f at C into h plus u of h into norm h, where u of h tends to 0 as h tends to 0. Let us mark or number this equation as equation 1. Now we can get something very similar using the differentiability of g at f of C. It tells us that limit h tends to 0, g of f of C plus h minus g of f of C minus the Jacobian of g at f of C into h whole divided by norm h is equal to 0. Therefore, if you define v of h to be equal to g of f of C plus h minus g of f of C minus the Jacobian of g at f of C into h whole divided by norm h, then we can observe that v of h tends to 0 as h tends to 0. Therefore, I can express g of f of C plus h as g of f of C plus Jacobian of g at f of C into h plus v of h into norm h. And notice that v of h tends to 0 as h tends to 0. And let us mark this equation, equation 2. Now we are prepared to prove the chain rule. Notice that to prove chain rule, we need to show that limit h tends to 0, g composed with f at C plus h minus g composed with f at C minus the Jacobian of g at f of C into Jacobian of f at C into h whole divided by norm h is equal to 0. Now let's try to understand the term g composed with f at C plus h. It is equal to g of f of C plus h. And using equation 1, I can expand f of C plus h as f of C plus the Jacobian of f at C into h plus u of h into norm h. But notice that this term, let's call it y, goes to 0 as h tends to 0. Therefore, using equation 2, I can write this as g of f of C plus Jacobian of g at f of C into y plus v of y into norm y. By substituting the value of y in the second term, we can rewrite this as g of f of C plus the Jacobian of g at f of C into Jacobian of f at C into h plus Jacobian of g at f of C into u of h into norm h plus v of y into norm y. Notice that in the numerator we are subtracting this term and this term from g composed with f at C plus h. Therefore, we can rewrite the above limit as limit h tends to 0, the Jacobian of g at f of C into u of h, notice that I am cancelling out norm h and norm h, plus v of y into norm y divided by norm h. Focusing on the term norm y and using the triangle inequality, we can say that norm y is less than or equal to the norm of the Jacobian of f at C into h plus norm of u of h into norm of h. Further, using slightly sophisticated linear algebra, we can conclude that the norm of Jacobian of f at C into h is less than or equal to some constant times norm h. This has nothing to do with the Jacobian matrix. This will be true for any matrix. And as this concept is not really within the purview of our course, I am not going to go into the details of this. But assuming this, we can see that the term norm y by norm h is bounded. Further, we know that as h tends to 0, y tends to 0, and therefore v of y tends to 0. Similarly, u of h also tends to 0. Therefore, this entire limit has to tend to 0, and thus we have completed our proof.